people to run it, and a small engineering team. And I realized one time we were all in a room together back in 2006, shortly after launch. I looked around, there's like 40 people in the room and maybe 10 on the phone, and I realized we're the flight crew. We're going to fly this thing all the way across the solar system, and we're going to be like a family by the time this is over. We're going to know each other so well, and that's exactly what happened. Now, this whole story, this is unabashed material. Put in a plug for your book. David Grinspoon and I published a book last year called Chasing New Horizons, which tells this whole story, which I've abbreviated. It goes right up through the findings of the Pluto flyby. It tells the whole political story of how it came to happen, the science story, some of the engineering breakthroughs that it took, and then the whole story, not just of how we flew it across the solar system, but how we planned the under-the-hood details of how you plan a flyby that's got to work because there's no backup. So if you have any interest in the story of New Horizons, this is a book I can recommend. By the way, I call it my 100 lost weekends because it took 2 years to write and rewrite and rewrite and rewrite until it got good enough that our publisher would accept it. But it won't take you 100 weekends to read it. In fact, when we first turned it in, it was about 500 pages long, and our publisher at Macmillan said, "It's a really good story. It's too long. No one will read it." And he said, "I'm going to hire a script doctor to come in and cut it." And we said, "Is that going to work?" And he said, "Oh, yeah, it works. We do it all the time." So 3 weeks later, he gives us back what I thought was kind of a butchered Chasing New Horizons. And it was so bad, I mean, that I remember being on the phone with this nameless script doctor who said, "There's no reason to bring up Clyde Tombaugh in this story, so I've cut him completely out." This is a story about the 2000s, not the 1930s. So David and I said, "No go. You can cancel our contract." They said, "We don't want to cancel the contract, but we also have a schedule to meet. You have 3 weeks to rewrite your book." And we did it. It was a bit of a horse race. We got it done. The book's a little under 300 pages. So let me go on, though. This is what I came here to talk to you about, is the extended, or what I like to call the first extended mission of New Horizons. And the way that it works in NASA is that when a mission finishes its primary objectives, if the spacecraft's healthy and there's good science to still do, and the price is right, then NASA will fund you for an extended mission. And some missions get extended over and over and over. Voyager's a good example. But many of the Mars missions, you just read about the Spirit and Opportunity project that was supposed to last 90 days that went for 15 years through a whole series of extended missions. So right after Pluto flyby, we proposed to do this Kuiper Belt mission, which the Decadal Survey back in the early 2000s had said is fundamentally part of doing this. And so we had a strong foundation. Spacecraft is healthy and full of fuel. And we had gone out with the Hubble Space Telescope and searched and found several possible targets that we could get to within our fuel supply. And then in August of 2015, just a month after the Pluto flyby, we went to Jim Green, who was on this stage yesterday. How many of you saw Jim here? Yeah, he was director of planetary exploration. And we told him why this particular one that we picked out, 2014 MU-69, should be our target. And Jim agreed. He's the person that has to sign off on it. And then in October of 2015, we directed the spacecraft through some engine firings off the post-Pluto course towards an intercept with this object, 2014 MU-69, which we later nicknamed Ultima Thule from the Latin. It means beyond the farthest frontiers. It came out of a naming contest on the web. So here's an interesting story. Is Jim here? Too bad. Maybe he's going to see this on video or whatever. But the NASA proposals, the extended mission proposals, weren't due until the 1st of April 2016. But it was very important to me to get on course for this target as early as possible. And so we went and told Jim, look, we want to get on course as soon as we can because the earlier you fire the engines, the less fuel it takes to deviate for the intercept, and the more fuel we can pocket for possible future missions. And Jim liked that story, and it was true, and approved it. But of course, the other reason that we wanted to fire the engines and get on course is, with a healthy spacecraft, a decadal survey, and already on course for intercept, what are the odds they're not going to accept your proposal? They're just going to turn it off, and it's going to make the flyby, but it's not going to do anything. So there. Hi, Jim. Okay. So our primary objectives. Now, I have to tell you, I'm going to talk to you about the flyby of Ultima Thule. But our spacecraft is actually being used as an observatory in the Kuiper Belt. That C8, the LORRI camera in particular, is capable of observing dozens of other Kuiper Belt objects, and we do it all the time. And we have capabilities by being local in the Kuiper Belt to do everything from what are called phase curve studies to light curves to searching for satellites that you cannot do from the Earth or from the Hubble or anywhere else. So we're developing data on other dwarf planets besides Pluto and on many small Kuiper Belt objects to go with the close-ups of Ultima Thule. And we use our onboard plasma and dust instruments to explore the heliosphere. In fact, currently we're the only spacecraft in the distant heliosphere because the two Voyagers have now exited into interstellar space. So we're the only distant monitor of that entire environment, and the capabilities that our dust instrument, which Voyager didn't have one, and the two plasma spectrometers, which are, no exaggeration, 1,000 times more sensitive than their equivalents on Voyager, built in the Stone Age of the 1970s, are just churning out tremendous data sets, literally 24/7, essentially 365 days a year. But I'm going to talk to you about the cherry on top, which is this close flyby of Ultima Thule. Our objectives were, this is the first time we'd ever been to something like this. Not just something this much farther out in the solar system, but an object that we know is a bedrock sample of the distant solar nebula, and which is a relic of the early days of planet formation. So for those of you who might not know, solid planets form primarily through a process where small things grow and grow to become bigger things and eventually become a planet. The comets are a great example of early material from that era and things that had to accrete from stones and boulders and so forth, house-sized rocks. And for example, Rosetta's comet, it's about 5 kilometers long, went through that process. But that comet and every other one we've ever seen has been heated repeatedly by orbits close into the sun, which changes their chemistry, which changes their surface appearance, which changes their structure. And so although they have a lot to teach us, they're very highly evolved. We'd never been out to the original birthplace before to see one caught in the wild. And Ultima Thule is not only primordial and always been cold, it's never been close to the sun, much better preserved. It's also enormous compared to a typical comet. Compared to Rosetta's comet, for example, this object is 7 times as big and 7 cubed times as massive. So it's just a tremendous opportunity to go and be able to study the geology, the composition of an object like this, to look for whether it ever had an atmosphere, particularly early after the formation days, to search for satellites and rings around it. And those were our primary objectives. Now, I want to give you an idea of how tough this is. I'm going to show this little 10-second video. This is planet Pluto, and we're going to zoom up on Sputnik, the big glacier, and there's Ultima, which is about the size of a typical mountain block on Pluto. So it was our job to hunt this tiny thing down in the darkness of the Kuiper Belt, 1 billion miles beyond Pluto, and get it right on the first try. And so we spent 3 years from the fall of 2015 to the fall of 2018 preparing plans to do this. And we were using every tool available to us. We had enormous amounts of Hubble time to track Ultima Thule and refine its orbit. We single-handedly, through the force of Mark Bowie on my science team and his chief lieutenants, along with many dozens of volunteers, developed a technique to actually get in the shadow of Ultima Thule, to do stellar occultations, to pin down its position and to search for debris around it. with a level of accuracy unlike anything that had ever been done before. Yes, people had done occultations of asteroids, but they are typically 40 times closer and 40 times bigger on the Earth than what we were going after. And through the use of the European Space Agency Gaia star catalog that gave us a very accurate reference frame, we were able to get 3 of the 4 occultations with good data and really pin down the orbit. And at the same time, we were planning these flybys that are all done remotely on the spacecraft. There's no commanding going on back and forth because the light travel times are so long. If you want to send a command to the spacecraft, it takes 6 hours from the time you launch it from a deep space network antenna till it gets up there. It takes 6 more hours to find out if it worked. So we put a pre-programmed, a canned sequence of activities on the spacecraft every few weeks, and it executes. And around the time of flyby, it's much more intensive activities. We spent years planning both a flyby and a backup flyby in case we had to divert because of hazards. And then we had predicted that that LORRI camera that Steve works on could, in a stretch, if we pulled out all the stops, detect Ultima Thule, this target the size of like greater Washington, D.C., but draped in velvet, black velvet, because we know its albedo, its reflectivity is very low, in the light of the Kuiper belt, which is 2,000 times fainter than when you stand outside this afternoon, that we could detect it from more than 100 million miles away. Now, that's the good news. The bad news is our direction of flight and where the target is in the direction of Sagittarius, which I think most people in this room know is the galactic center, the densest star fields in the sky. So we were looking for this faint little ember at 22nd magnitude in August of last year against these star fields that are ridiculous, just completely obliterated with other stars. And we had predicted exactly which pixel Ultima Thule should appear in if we had the navigation right. And if it was off even 1 pixel, it would be bad news for our fuel supply. So we woke the spacecraft up from hibernation in June. We got a lot of data off the spacecraft, cleared the recorders, erased, got ready to fill them up with Ultima Thule data. We conducted some other science, some tests on board the spacecraft, made sure everything was good to go. Then in August, we began using the LORRI camera to spot Ultima Thule for optical navigation purposes. And that was very successful. Here's the star field. Actually, no, this is not the star field. Here's one little tiny piece of the star field in the middle of the center of the field of view. And we'll see if I can make this work. Okay, watch Ultima Thule appear and over several weeks cross the field of view. Can we do that? This should run. Oh, here it's going to go. You see Ultima Thule getting brighter as we get closer, right? Emerging out of that little star cluster. There it is. That's a period of about 90 days, by the way, all that relative motion. Anyway, it did turn out to be dead center near that exact expected pixel, and we tracked it, and we did course corrections in October and November and December to get there. This is our plan, was to fly over to the north, to the celestial north of the target. We come at it with the sun at our back at what we call low phase angle. So the sun is almost shining directly on the target, and we're coming out of the direction of the sun. And our goal was to approach much closer than we came to Pluto. In fact, 3.5 times closer, which made it more challenging. Not only to navigate there, but then to get all the observations right, because the tolerances are lower as you go closer and closer. You have to be more and more exacting to make sure that your fields of view are on the target, not half off the target or all the way off the target. So we plan to fly as close as 3,500 kilometers. Let me put that in perspective. The closest point to Pluto was about as far away from here as Tokyo. And for Ultima Thule, it was about as far away as Los Angeles. So dramatically closer. And then with the LORRI long-range camera, our highest resolution imaging at Pluto was 80 meters per pixel, and we plan to get down to about 33 meters per pixel at Ultima Thule. And we did. We put together a very carefully choreographed 12-week observation program with a very high-intensity 9 days, and within that, 1 day of furious activity when we were close enough to map the target map its composition, to search for satellites, search for rings, search for past or present atmosphere, see if it interacts with the solar wind, take its temperature, try to measure its radar reflectivity. And this was a computer sequence that between design and then refinement and test and audit and everything that went into it took 3 years, but we only had one chance. And this flyby really was a stretch in every way. I showed you the size of Ultima Thule compared to Pluto. It's tiny. To try and track that down was an enormous challenge all by itself. And we didn't know if it would have a hazard debris environment, a lot of stuff left over from the formation days, that flying past it at 32,000 miles an hour could be fatal to our spacecraft. So we had to put in place a hazard search. And we had a hazard search team, and they had 7 different simulations that were multi-day simulations of how we would reduce the data and make decisions about whether we would have to divert or not. The lower lighting levels meant the instruments had to strain much harder to develop the signal to noise. And they didn't have as much time because the target's so much smaller, you have to do everything closer in. And then the communications times that I spoke about earlier, 6 hours each way, 12 hours round trip. Compare that to Pluto, 9 hours, which itself is a long time, but just that everything's getting harder. And then the spacecraft has lower power levels because the plutonium is generating less heat and therefore less electricity every year. And that made it harder because it meant that we had to very carefully choreograph what's turned on and what's not at any given moment to never get above that 190 watts that the RTG, the power generator, could produce. Because if you ever go over that, the spacecraft browns out, and then you will lose observations while it's recovering. So all of those 5 factors conspired to make this dramatically harder to do. And as I said about Pluto, it's the same for everything New Horizons does. You get one chance. There's no way to do a U-turn and come back. There's no New Horizons 2 following a few months behind. You get it right or you don't. And this is what you saw if you followed any of this flyby. It all worked, and you saw our press conferences and standing ovations, and maybe you saw some media and cartoons and things like Prickly City here. But I thought I'd take you back behind the scenes and show you what it was like. So I'm going to show you a few pictures on the behind-the-scenes part. And these 3 are all made in our geology and geophysics back room at the Johns Hopkins Applied Physics Lab. And the first one I'm going to show you is live, taken the moment, not a minute later, but the moment that the first high-resolution image of Ultima Thule, not a smudge or a fuzzy thing, but the first really good image went through the computer processing and popped up on the big screens in the geology and geophysics room. And the people in that room, like the rest of the New Horizons crew, have been working to make this work for 3 years straight. And here's the first image at 3 in the morning. And you can just see the emotion in that room. And then we had this amazing object that I'll tell you a little bit more about in a couple of minutes. Here's another picture. These are the leaders of our the guys that were navigating us to the spacecraft. And when that picture showed up with Ultima Thule dead center, the whole thing broke out in hugs. And then within a few minutes, of course, all the nerds are on the computer because it's time to get down to science. This is what we saw on New Year's Eve, first resolved image of Ultima Thule, 21 miles and 33 kilometers in length. We later refined that to 35. We called it a bowling pin. And we had already had good information from the stellar occultations that it was either going to be a close orbiting binary or what we call a contact binary, in which the 2 objects that had been orbiting were now physically resting on one another. And we still couldn't tell one day from the flyby, but very quickly after that we could. So meet Ultima Thule. This is the real deal. You are looking at history. 4 billion-year-old object from the birth of the solar system. It's about 20 miles long, as I just said. If you're familiar with Rosetta's comet 67P, Churyumov-Gerasimenko, it would very nicely fit in just this hole in the ground on on Thule. And we named the lobes Ultima and Thule, as I'll show you in a minute. And one of the things I want you to notice right off the bat is how undamaged the two objects look. Right? They look completely intact. The typical collision speed in the Kuiper belt for this orbit population is about 300 meters per second. So if these two objects had formed far apart and come together in a collision like that, they would completely shatter. They must have formed very close together because they had very low relative speeds. We can't find fracture zones. We don't see any strong signs of violent deformation. So that tells us that their merger was a gentle process. I'll say more about this in a few minutes. But they must have literally formed together, like peas in a pod, and then through some process, which I'll talk about, come together into gentle contact. And we use the term docking a lot because had to be so slow that it was almost like spacecraft docking. And when I put the first paper in, it's going through refereeing to Science magazine, they came back and the editor said, don't use that term docking. That's what pilots do. It's not what inanimate objects do. So it's all about gentle mergers. Here's a little bit of terminology. The big lobe we call Ultima. The little lobe we call Thule. I mean, we don't have much imagination. The object was Ultima Thule. It's 3 in the morning. We're all tired. All right, we'll split it up. The neck or the collar between the two objects where they're joined is this amazing bright ribbon of material which we do not understand, but which is very prominent, and there you see it. Here's an approach movie made over about a day, and you can see that the rotation axis is pointed nearly directly back at our direction of flight. So it looks like a propeller spinning. We derived a period for this. It's 15.92 hours, fairly typical of small Kuiper belt objects like that, but the polar obliquity, the fact that its pole axis is tilted 98 degrees, just about like the planet Uranus, right, on its side, is an important clue to its formation. When we look in more detail on the surface, we see all kinds of interesting albedo markings. Now, everything you're looking at here is dark. Remember I said black velvet. The typical reflectivity on the surface is about 7%. 93% of the light that falls on Ultima Thule is absorbed by that surface. But there are places that are brighter and places that are darker, and they range from about 5 to 12% reflectivity. And here in an image where we've stretched the contrast so you can see it better, you can see there are different classes of these bright features. There are ovoid or more or less circular bright spots, and there are a lot of them if you look carefully. Some of the most prominent ones are pointed out there. There are what we call bright curvilinears. So they're elongated tracks on the surface that are bright. The most notable of which is the neck itself. But it doesn't show up as well here, but I'm pointing at some of them. It's much better on the little screen down here. And then, and this is going to be even harder for you to see, but there are broad zones that are higher in reflectivity than the material surrounding them. And since we see many of each of these three types, there's got to be some physical process that creates each of the three, which we would like to understand. And there are also dark zones. There are only 1 or 2 dark spots, and there are no dark curvilinears, but there are some dark zones like the one that's shown there. Let's talk about cratering. We normally use cratering to understand the age of objects, and when a surface is light,
good morning, everybody.
It means it must be young. Unfortunately, because we came straight out of the direction of the sun and the phase angle was very low, meaning the sunlight was shining directly down on the target, there weren't many shadows to help us pick out craters. And we have a couple of cratering experts on our team, Stuart Robbins and Kelsey Singer, and they've been doing exactly that. We see groups of craters in a line like that we don't think are actually due to impacts, because you'll notice not only are they all correlated together spatially, they're in a line and they're all the same size holes in the ground. Those are much more likely to be collapsed pits or sublimation pits that formed endogenically, not exogenically. But there are lots of things that might be craters on the surface. And we have completely enumerated all of them and measured their diameters, and we can pretend that they're all craters. What if they're all craters? So Kelsey's done that, and I'm going to put these plots up. These are nerd plots with log plots, but what's plotted here, without understanding the scales or what an R plot is or anything else, she's taken 4 different measures of confidence for every potential crater, from I'm really confident it's blue down to it's, are you kidding me? and plotted the number of craters as a function of size. Okay? And you can see that all 4 results are roughly the same, but what's more important is over on the right, those red lines represent the kind of distribution you would expect if the region of space out in the Kuiper Belt where Ultima Thule orbits was in what we call collisional equilibrium, where it's a shooting gallery like the asteroid belt. And you can see that the plots that Kelsey's made from the actual data don't look anything like that. They look more like the blue lines that were the prediction for what we would find if the region near Ultima Thule was like what we found at Pluto at the inner edge of the Kuiper Belt, with a dearth of small kilometer-sized and smaller objects and nothing like collisional equilibrium. So we confirmed that result. And then, we try to eke everything out of the data so we can plot the profile around the limb of all the topography. And we can subtract from the distance from that profile the general shape. So you take out the low frequency information that's just about the more or less figure 8 shape of the target and find out how tall the mountains and hills are that are protruding above the surface. And here we see the Ultima lobe on top and the Thule lobe on the bottom. The Ultima lobe has about 1 kilometer of relief. It's about 3,000 feet. The Thule lobe has about half that. Taking that and knowing something about the local gravity, which we can calculate or at least guesstimate, and guesstimating the density, we can actually derive some interesting constraints. One of them is a constraint on the strength of the material that it would take to hold those features 1 kilometer high up over billions of years without them slumping under their own weight. And what we find is that the strength of this material could be as low as talcum powder, right? It could be like a fairy castle structure. We've been making geological maps, and this is a complicated pair of objects. We hit the jackpot in terms of the geology. There's a lot it has to teach us, but the thing that I want to concentrate on here today, before we turn to questions in a few minutes, are the things that those arrows are pointing at. I'll go back to the geology map and point out that on the big lobe Ultima, there are 8 of these roughly similarly sized regions that abut one another. Typically, their interfaces are bright material, like I showed you earlier. And what could they be? We have a lot of ideas. Those could be the elements out of which it was made. Or they could be the result of some sort of subsequent evolution of the object, for example, by bottling up the heat of radioactive decay from aluminum 26. Or it could be other things. And we're still working on that, and some things are working out and some things aren't. It's early days. All this data is only a couple of months old. But take a look at the other lobe. You don't see any of that, those same size pieces on the Thule lobe. Why is that? If they were formed together and they have the same reflectivity and they merged at low speed, meaning they were formed from the same part of the nebula, why doesn't Thule look anything like Ultima? Well, it just might. There's some actual hints of similar units on Thule, but it looks like this big feature, the big crater, basically obliterated and resurfaced a lot of Thule early in its history, and it's just masking what's probably beneath. We make color images with the Ralph camera on board. There's in the top left, you see a Ralph color image. It's not nearly as high a resolution as a LORRI panchromatic or black and white image. So what we do in the computer is we take the LORRI high-res image and the Ralph low-res color, and we drape one on top of the other, and you get the result on the right. And then if you look further to the right where it says most prominent color variations, what we find is the 2 lobes are not only similarly reflective or unreflective, but they also have the same color to within the error bars. And it's only when we stretch and stretch and stretch the data that we can start to find a few places, like are pointed out in those arrows, that are not quite the same color. And the way that we do it is we use red and blue to indicate the different spectral slopes, but actually nothing on this surface is blue. Everything is red or less red. And when I say red, I mean as ultra red as anything in the solar system. And the stuff that's less red is still very red. We've also got compositional spectra now, and we have tentative identifications of water ice, which is not surprising, and methanol, which is very common in protosolar disks, and may have been from the material out of which our protosolar disk was made. Here's a little better look at the color. You can see that the only regions that really look a little bit different are basically the neck, this thing we call the thumbprint. It's kind of bluish here, but remember, just less red. And then this canyon or gash, which is also blue. Don't believe anything around the limb because that's just an image processing artifact. But what's most amazing about Ultima Thule, other than just thinking we went 4 billion miles and 4 billion years in history, but scientifically, what's most amazing is the shape of the object. First, a contact binary. Secondly, an intact contact binary. But what really surprised us as we started to get more and more images in from different angles was the fact that these two lobes are not spherical. They're like pancakes or discs. And you can see that very clearly in this sequence where we're taking the images and rocking them back and forth. No one expected that. There's no model that predicted it. How that formed, we got a lot of ideas. And we can talk about that in Q&A. But it really must be a very important clue to the origin of the object. So here's our best computer-generated shape model. And I realized that to some people, the one in the lower right does look like the Starship Enterprise with an engine nacelles taken off, but it's not. This really is a very surprising object. All formation models generally produce things that are roughly equidimensional. And you think of all the asteroids that you've seen. The fact that this is a bilobate or object or contact binary is alone amazing. But the fact that they are so thin in that third dimension is also amazing. And get this. Look, you might have noticed this, but the three principal axes are also very well aligned. That's another clue. And what probably happened, I need both hands, is that as they were orbiting one another, their mutual gravitational tides caused the objects to co-align and lock up in that stable configuration. They didn't form like this, or like that, or like this, or in some crooked way. They literally merged as if someone, can I say it, docked them. Right? Now, please don't tweet that. I once gave a talk in Canada to the Royal Astronomical Society of Canada after the flyby of Pluto and referred to the geology by saying Pluto is alive. And the next morning, I'm getting calls from NASA headquarters. What did you tell them? I meant geologically alive. Okay. But this is an amazing, if you do it in a computer and you calculate the odds this would happen by chance, it's like 1 in 100. So it's almost certainly strong evidence of this tidal evolution that caused the object's principal axes to align before they actually merged during the late stages of that orbital evolution. Now, let's talk about the merger itself. And I don't know how to start this video on the left from here. But this is what happens when you make a collision at 10 meters a second, which is like a car crash speed. The two objects basically just glance off each other, and because that 10 meters a second is high compared to either of their escape speeds, they just go off to infinity. And by the way, this is a very sophisticated model developed by Derek Richardson at the University of Maryland and his students, one of whom is shown there, that includes tens of thousands of finite elements and he correctly represents the strengths of the objects, which we put in as a free variable, their mutual gravity, and friction in the collision. So this is a lot of fidelity. It's not just a cartoon. This is a calculation done on a supercomputer that takes days to complete. So what if we make the speed slower, 5 meters a second, like a fender bender? That's the next one, which I hope we can show you. Maybe the back room can help. So 5 meters per second, what happens? Now the collision speed is low enough. We need to start that, yeah. that they're not going to fly off to infinity. But on the other hand, the way they merge doesn't look anything like the Ultima Thule that we see at 5 meters per second, with all that physics in there correctly represented. What did happen? Here's what happens at 2 meters per second. They dock. I know science thinks it's a 4-letter word. Okay, anyway, so we think we've got a handle on what's happening. How did they get to such low speeds and such slow rotational speeds? What was probably going on is there was a large cloud of material out of which these are the two dominant players, and they were ejecting other objects from the swarm, and in doing so, shedding angular momentum and orbital energy, and hardening the binary, meaning they were moving towards one another as a result of ejecting the smaller bits and pieces. And here's kind of a cartoon view of how that might all get put together. So there's the swarm on the left, there's the pair that are now close to one another and interacting tidally, and then they merge or dock. Well, whatever it is, I can tell you that we hit the jackpot again, just like at Pluto. Ultima Thule has a tremendous amount to teach us about the formation days of the early solar system, and we just couldn't be happier. And we're just like kids in a candy shop with the data. The data transmission itself will continue through late next summer to get everything to the ground. And the analysis and paper writing will also continue. We're currently funded through 2021 to finish the first extended mission, and we'll propose a second one. But we have a long way to go. Every week, new data lands on the ground from one instrument or another. And I like to liken the process to being ER docs. As a new patient comes in, you just triage the patient and move them along, and then the next patient's coming in. In the same way, we get new color data or new high-resolution data or new plasma data or new this or that every week, and we make a quick analysis of it, and then we move on. And so we're only scratching the surface of what's there to do, and when you combine that with the fact that 80% of all the bits are still in the spacecraft, that we've only been at this for 3 months out of 20 months, stay tuned, because there's going to be a lot more to come out of this flyby and its results. These are just some of the mysteries that we've already identified about how the thing formed as a binary, but how the two individual lobes formed, how they got aligned, the strange albedo markings, the nature of those mounds or like-sized units on the ultima lobe, the degree of cratering that we're still uncertain about, and the origin of the color variation across the surface. So we got a lot of work ahead of us, but we're very happy about how well it all turned out. If you want to hear about New Horizons and what might happen next, I'll say a few words about that. The spacecraft is still very healthy, 13 and a half years after launch. We're using no backup systems owing to failures. Sometimes we use backup systems for engineering reasons, but we don't have anything broken on the spacecraft, and all 7 scientific instruments are working perfectly. The power supply on board can run us into the mid or the late 2030s, at which point we'll be more than twice as far from the sun as we are now. We'll still be in the Kuiper Belt until 2027, and we have just about exactly as much fuel left on board as it took to target Ultima Thule. So we would like to try and get another flyby, and we think we got a fighting chance to do that. You remember I said that we're very happy that when we got off the Atlas on the first day of flight, that it delivered us much more precisely. So we pocketed a lot of fuel that we didn't have to use in initial course corrections. And that's what's made it possible here, literally 13 or 14 years later, to think that we've got a good shot at one more flyby to see another Kuiper Belt object, probably a couple of billion miles further out still, that we have not discovered, that we will have to search and hunt down, and which will be even harder than what we just accomplished. But the New Horizons team is an amazing group of people and very dedicated to every aspect of this project. And so, onward, New Horizons, and thank you very much. Oh, it's a stool. I can actually sit and take questions if there are any. right in the front. Yes, sir.
So when you were talking about it being like talcum powder, like covering, is there any sense of how deep it is? There's that
It
one
might.
looks like a crater rim on the center of Ultima.
The very surface is probably churned up by micrometeorite impacts, and is certainly likely to be like almost strengthless. But it could be that the entire object is that way, that the entire structure is gossamer. Who else? Right there, yes, sir.
This is back to Pluto. I can't imagine, I wish you would describe what happened when you had the computer reset just before you arrived.
Okay, so the question was, he said, let's go back to Pluto, and I can't imagine what it must have been like when you had the computer reset. For anybody that doesn't know, 10 days before we arrived at Pluto after more than 3,000 days in flight, the spacecraft went offline. I get a phone call on my cell that we lost contact with the spacecraft. This is actually the way that our book begins, is on that afternoon, and what that was all about. Because I also couldn't believe that this was happening after a flawless 3,000-day flight and 10 days out. But it was a massive and heroic effort by our team. It was on the 4th of July, by the way, which is, everybody expects fireworks on the 4th of July. Not this kind. And so we have a phone tree, and phone calls started going out within minutes, and the entire team assembled, the engineering team and the flight control team and others, and we went into a round-the-clock 3-day effort. And it was just like you saw in the movie Apollo 13. People were sleeping under desks, and they were going with cat naps for 3 days and eating out of candy machines. And we had, help running out to local fast food restaurants. And they basically did 6 months of work in 3 days to put Humpty Dumpty back together again. It was an amazing, amazing effort. And they saved the day. It could have been New Horizons sailing past Pluto and having no return. Yeah, okay. This lady.
Hi.
Hi.
You and your team have done so much to inspire people with Pluto and New Horizons. What would you like educators, science communicators, others to be able to continue to communicate and share out for you and your team?
Wow. So you asked what should you're an educator. Yes. Thank you for your work. What should you communicate? Well, I probably have a long list, but I'll just give you 3 items. First of all, scientific discovery is something that's unique to human beings on this planet. It's something it turns out we're really good at, and I hope that you will engage and enthuse your students to go into STEM careers, because we need more of that to power the economy. Secondly, New Horizons is a risk-taking mission in many ways. We took the risk of not being able to meet schedule or cost or not succeeding technically. No pain, no gain. It'd be great if you could teach about prudent risk-taking, right? And then there's that thing that I was just being told about in the hall today by somebody who says that teachers are required to teach that there are 8 planets, which I have a problem with, since we're discovering... And not just 9. It's not about Pluto. We're discovering that the solar system was really good at making lots of planets, most of them small. And it's completely ironic that astronomers are afraid of large numbers. I'm going to be giving actually I'm on the 29th of April in Washington, D.C. at the Philosophical Society of Washington. I'm debating Ron Eckers, who was the IAU president in 2006. Shred. Okay, let's see who's next. Dead center, yes ma'am. And I'll come back in the back rows in a sec.
First of all, I loved your article in Astronomy in which you gave an argument for not doing away with the term planet. That was classic.
Well, thank you, and thank Dave Eicher here, from the editor of Astronomy, who's also of the same opinion.
Do you and David have a follow-up book plan, maybe called Following New Horizons?
We don't, as a matter of fact. But the book, Chasing, is going to be released as a paperback in May, on May 22nd. That's the next step, and then we'll see about a second edition with some updates. Well, we could do the director's cut, right? Because we kept all that. There's a lot of good stories in there. I'm going to go further back in the room before I come back in the front. Yes, ma'am.
Hi, Alan. Is New Horizons collecting any data or imaging on its journey to its next potential object?
Yeah, we do that all the time. The in situ, or the plasma and dust instruments, operate round the clock. We very rarely turn them off, very rarely, like 1 or 2% of the time. So they're collecting this amazing transect record across the solar system. And then we use the LORRI camera to look at other Kuiper Belt objects and dwarf planets all the time. We just finished a suite of doing that, and we also did some look-back observations of Pluto last month to look for whether the hazes that are particularly easy to spot from behind have changed significantly over the intervening almost 4 years. We have our next set of Kuiper Belt observations scheduled for a really intensive period in late August and then in the beginning of September. Okay, who's next? How about way over there? Yes, sir. Huh? Say again?
I watched the live presentation on Jan 1st when you guys were expecting the countdown.
Oh, great.
Gave me a lot of goosebumps, so thank you for that. It was an amazing journey. So, 2 quick questions. How long do you think before we can keep going on with this project, like far in the future? Do you expect it to image after it goes interstellar? New Horizons. And the second one is there a landing mission is also coming?
Is there a landed? Okay, let's do all that. So first, future of New Horizons. I don't think there's any reason New Horizons shouldn't, from a technical standpoint, be able to operate into the late 2030s, maybe longer. Originally, we thought we could operate the mission into the 2050s. But when we were developing New Horizons, one of the things that came out of the blue, and some of you might remember this from the news, but it's a while back and it was a little obscure if you weren't in the middle of it, was that the institution that produces the plutonium dioxide that fuels the power generator is Los Alamos National Lab in New Mexico. And in the early 2000s, there were 2 shutdowns of the lab, one due to a safety violation and another due to a security violation. Neither had anything to do with New Horizons, but they had great consequence. And there was a point in time when we didn't think we could get enough nuclear battery fuel to do the mission. We really thought we couldn't. And NASA really jumped in and helped and found leftovers from other missions and some calibration supplies that all went in. But we ended up launching with about 50 watts less than spec for the nuclear battery. I said 250 watts, spec is around 300. And that works out to about 13 years of mission life. So it used to be, and when we proposed it, it was going to be kind of a stretch goal to get to 2050, and now we'll be lucky if we get close to 2040. However, there's lots of good science, and we're the only spacecraft out there to do it. And we are going to propose to NASA next year to revamp the flight code on board the spacecraft so that we can use the LORRI camera again to actually hunt our own targets from inside the Kuiper Belt. Nothing like this has ever been done except in a sci-fi movie. It's true. And if we can pull that off and we can find something over the next 8 or so years before we leave the Kuiper Belt that we can reach with our fuel supply, it will necessarily be a flyby on warning. Remember, we could only spot Ultima Thule about 5 months before the flyby. We can strain a little harder. We have a new capability on the LORRI camera. Maybe we can see things 6 months in advance, but what it means is we'll have to write the flight code for the flyby and put it on a shelf, fully tested. And then when we spot a target and confirm and fire the engines to go there, we'll have to pull that off the shelf and implement it in a matter of weeks, which will be pretty exciting. And nothing like that's ever been done before, except in the movies either. So I'm pretty excited about developing all that and trying to pull this off. There's no guarantee it will work. I mean, I'm sure we can write the software, and but there's no guarantee the Kuiper Belt will.
I'm still here.
Give us targets within our fuel reach, but you know, everyone in this room and everyone in this country, you know, paid to get New Horizons out there, and it's perfectly working. So we want to get the most out of it, and that's our plan. And if I have anything to say about it, we're we're going to try very, very hard and hopefully succeed. More questions? Right there, yes, in the red. Oh, it's just some artist. It's not an engineering diagram. Don't worry. We didn't discover any new physics. Okay, let's see. Are there people in the back that have their hands up or not? Is it only people in the front? Okay, yes, that's as far back as it can get. Yes, sir. Dead center, standing up. Right. Only from about the distance of the Earth's moon inward, which really just means the last couple tens of hours, right through the flyby. And as soon as we pass close approach, then we're looking at the night side, and there's not much to see. It's in darkness. Well, all the very best high-resolution data sets, which are now on the ground, by the way, all those were made in just a period of about 4 or 5 hours. And we had 10 close approach observations made during that period of time. Okay. With the iPhone? Right. Mm-hmm. There is. So he asked whether there's an archive of New Horizons data that he can get his hands on. And this is the way it works. For LORI images, which are easy for us to deal with on the fly as they land, we put them up on our project website, which requires no password, every Friday if there are new LORI images. They're there, and you can click on them and download the JPEGs every Friday. For everything else and the LORI, a very carefully calibrated and highly documented version of the data goes to a system called the PDS, or Planetary Data System, and is archived for people to use now and in a century. And every planetary mission is required to do that. And it's a very careful process. You don't just turn things in. Then they have peer reviewers, and they give you homework assignments, explain this better, or sometimes they find a mistake in a calibration or something. And so we end up, when we're done with each step in this process, with something you can really count on for the ages. And New Horizons, our next data delivery is in June, and then the one after that's in October, and the one after that's in April of next year. And it continues every few months as long as we're funded to do it. And anybody can get an account on that system. You don't have to be a NASA person or a card-carrying planetary scientist. Yes. I think you asked 3 questions. The answers are yes, yes, and yes. And in fact, this kind of process has been known or predicted in computer simulations of planet formation for years. So we're basically providing the confirmation that something like that actually physically happened in the solar system as predicted. Okay, let's go way over on the other side of the room. And how about in the front row? Yes. Okay, so how come we don't have a Voyager plaque or a Pioneer plaque? You're looking at the reason we don't, because people wanted to do that, but when I talked to people that did it for Voyager and for Pioneer, I found out how involved in terms of political correctness that became. And we were really under the gun for schedule, and I thought it was better to get a spacecraft to Pluto than get a spacecraft maybe with a plaque that didn't go to Pluto, or maybe just sitting in Florida, not able to launch. So I vetoed that whole idea. Now, we did put 9 things on the spacecraft we call mementos, and I've written about it before. Most famously are some of Clyde Tombaugh's cremains, a couple of American flags, a couple of CD-ROMs, things like that, but no specific message meant for others. However, there's some clever ideas about how we might do that in the future, and you'll just have to stay tuned. Okay, right here. Almost certainly. There's a large body of evidence now that the giant planets rearranged where they were in several different ways in the very earliest stages of the solar system's history, and that because they are so muscular gravitationally that they caused other objects to either be ejected, like to the Oort cloud, or to be pushed out. In fact, modern planetary formation theory has Pluto forming about half its current distance to the sun and having been pushed out. We have very strong circumstantial evidence for that. Somebody asked me, and I forgot to answer, if there will be a Pluto lander. I'll be very happy just to get an orbiter, but and we're working on that. But over time, when there are more missions and we can get down on the surface and even the subsurface, we can develop specific information that'll tell us if these dynamical models are correct. What else? We have time for maybe 3 more questions. Yes, ma'am. Well, she asked if I have any advice for late bloomers. I have a story and some advice. The first story is that I was a late bloomer, so I'm sure it can be done. I first went to grad school and studied aerospace engineering, and I went off and worked on spy satellites and some NASA projects, and over time found that I liked science better, but I had a house and a baby, and it wasn't very easy to go back to grad school. Eventually, I found a way, and then graduated about 8 years later than my cohort to become a scientist and start over at the bottom of a different field. So it can be done. But my best advice, if you want to be involved in the space enterprise, almost every line of work there is represented in the space enterprise. And whatever your skill set is, whether it's engineering or science, or whether it might be accounting and project planning, or whether it might be public affairs and public engagement, there are hundreds of career specialties. So I would just say find where your heart is, what you like to do the best, and go do that. Don't force yourself into the thought that everybody in this business, are the ones that do the math the best. Okay, we got lots of those. Our new NASA administrator, Jim Bridenstine, a lot of people thought, what are we doing hiring a congressman to run NASA? I never thought that. First, I knew Bridenstine for a couple years, and I was super impressed with his abilities and his background. But secondly, last I counted, NASA has 18,500 engineers and scientists. What difference does one more make, right? What I thought we really needed was somebody who knew how Washington works, and he's turning out to really be doing that very well. So that just shows you non-traditional skill set can be very important. So follow your heart. Right here, yes. Yeah, so the question was, did Lori record all the images you see on Pluto? Not at all. The Ralph color camera which also has black and white, is also used. It has a wider field of view, which is important for some kinds of observations. And LORRI has no color capability. So anytime you see an image of Pluto or its satellites or Ultima Thule that's made in color, that's a Ralph image. I think I can do 2 more. Okay, right here. Yes, sir. Yeah. From Pluto. From, yeah. You know, so the question is whether there might be big discoveries coming out of Pluto data in the future. I can guarantee you there will be, because it's only now, we're only a year and a half since the last data came to the ground. And then the way it works in our business is people who look at the data have to write funding proposals. By the time they write them and get them approved and get funded, a year or 2 years goes by, because sometimes it takes a couple tries. Then they start their work. And all of the really detailed stuff for formation modeling, for the evolution of the geology, for the evolution of the atmosphere, all those things are just now getting cranked up by experts all around the country who've been funded to go milk those data sets. And even today, 30 years after Voyager did its thing at Neptune, Mark Showalter, who's on the New Horizons team, just discovered new satellites. It's just amazing. So I'm sure that a lot more is going to come out of it. Okay, last question. Right there, yes. If I had the chance, that's the wild card. That's the wild card. So, you know, in retrospect, I'm really glad that we didn't succeed at getting a Pluto mission earlier, because we would not have had the same amazing instruments. The technology, even in the early 90s, was not the technology of the early 2000s. And, you know, you could always wish that we had more money and could have flown more instruments, but I think really, for a first mission, that New Horizons did it very well. And if I could really do it over and have any one thing, it would have been to have had New Horizons 2, so we could have seen the other side of Pluto and its moons. So that's my answer to the last question. But I'll be around for a few hours out in the gym over there where all the exhibits are. And so come and find me if you have more questions. And thank you for having me to NEAF again. Thank you.
Thank you. Alan, thank you very much. A big thank you. Alan Stern, thank you.
Thanks, Vince. We're going?
There is not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every mood, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be and ought to be, in a modest, personal way, an astronomer. For stargazing is a great medicine for the soul.
Five, four, three, two, one, zero.
Today I want to take you on a journey to the outer reaches of the solar system.
Mission Operations Manager, as a mom.
It's great to be here. Thank you. Wow, there are a lot of you. What a great conference.
Friday, I was a launch chief engineer, and that means that I'm really busy with the mission.
No one has ever seen before.
My name is Grant Regan, and I live in Los Angeles. I first got into astronomy. Just as a kid, I was always interested in the sky. I'm situated on the west side of LA, and the light pollution is pretty bad anywhere in LA. And even if you drive an hour and a half out, you'll still see the light dome of LA in the south or in the north, depending on where you go. The Rossa 8 has a very fast system, and because of that, you can take images that would on other scopes take up to like 30 minutes. You can take on the Rossa in a minute or less. And that difference is huge, because what matters is that you can take short exposures but get that detail and not have star trailing or anything like that.
And basically I'm taking this from a heated car when it's almost freezing outside. There's a telescope right there, so I'm just remote control using it. This is just a lone exposure. It isn't even a raw image. It's not processed at all, so once we process these, they're gonna look amazing.
With astrophotography, it's not just taking a shot and saying like, this is what's on the sky. It's really taking multiple shots, stacking them together and putting your own vision on that and showing how you see the sky.
Hello there, I'm Lonnie Ouija with Celestron, and we're here live today at NEAF, and I thought I'd show you one of our new products. So what you're looking at is a brand new Roe Ackerman design. We call it RASA. This is an 8-inch f2.0 imaging system. Now, one thing you'll notice about this, if you look at where we place the camera is designed to go on the front of the telescope. What we've done is we've taken a standard design and turn it into a RASA design, and that means the light goes through the corrector plate, it hits a primary mirror in the back, it's reflected back up on the camera, and we get very fast wide field images. If you notice the camera we're using, it fits inside the objective so we don't block any of the light. This has been a hugely popular product for us. We're unique in this design. If you're interested in wide field imaging, if you're interested in the sky surveys, if you're just interested in a good fast way to get started with astronomy, the Roe Ackerman is new. If you notice, we also have our new focuser on the back. This is something that's nice to have when you're doing astronomy and astro imaging. This will have steps that you'll be able to do the micro focusing needed to control a fast imaging system like this. We're very happy to have it here at NEAF, and come on by and take a look.
Hi, my name is Jeff Norwood. I'm the owner of Camera Concepts and Telescope Solutions. We're based in Long Island, New York, and we are, I'm proud to say, one of the supermarket vendors of telescopery. We sell everything and everything, from accessories to screws and bolts to things you need at star parties, all the way up to Takahashi's and you name it. All the rest of that. So at our booth here, we've been coming here to NEAF for over 20 years. We basically bring the entire store with us. So we've got lots of goodies. And of course, everything's on sale, great deals. Our website is www.cameraconcepts.com. Please visit us. We support what we sell. We've got experts in the field on staff to help you with astrophotography or all your visual aids that you might need. So thanks a lot, and bye.
Hi, I'm Kelly Beatty from Sky and Telescope. I'm a senior editor on the staff. I've been on the staff of Sky and Telescope since 1974, hard to believe. But I'm still having fun, and why wouldn't I? We're a very important part of the amateur astronomy community, just as NEAF has become a kind of essential go-to place each year for many thousands of people in the amateur community. We're here, we're one of the co-sponsors of NEAF, and we are dedicated to being a major part of that. You know, people think of us as just Sky and Telescope magazine. We're actually much broader than that in a couple of respects. One thing is we do a lot of outreach. We provide a lot of materials for amateur clubs across the country when they need materials to distribute at their star parties and such. And we also do some products that are maybe not what you'd expect from a magazine. I've got a couple here. We have a whole line of globes that we sell. They're really great. This one, for example, this black beauty is our celestial globe, which shows all the stars in the sky down to 5th magnitude. And then this is our new one, just about to be produced. It's a globe of the Earth, obviously, but it shows all total solar eclipse paths until the year 2100. So if you're the kind of person who likes to plan ahead, this is just the globe for you. You'll know where to be in 2024 and beyond. The other thing we do a lot of is tours. Speaking of those eclipses, we've actually got a whole bunch of tours that we do all over the world. We just had a tour finish in Finland to go see the auroras. It was very successful. This summer we have a tour of Chile coming up for a total solar eclipse. We've got an observing tour planned for Australia that is just going to be killer. So for all these reasons, Sky and Telescope sort of considers itself the essential guide to astronomy. And again, we've been at this for 75 years, so we really have a good handle on the amateur community. We're from the amateur community. We'll always be a part of it. And we are so grateful to the organizers of NEAF, Ed Seaman and the rest of the crew here for welcoming us every year and being such gracious hosts in this amazing setting where the sky is really the limit. So thanks very much for the opportunity to chat, and we'll see you here next year.
Hey everybody, Scott Roberts here from Explore Scientific, and we're here in Suffern, New York at the epicenter of the universe, the Northeast Astronomy Forum. This is a great event that happens every year, and it is in fact the world's largest astronomy trade show. Every manufacturer is here. You've got telescopes, you've got eyepieces, cameras, observatory domes, and tons of software. Some of the greatest retailers are here as well. You've got, Woodland Hills and High Point, Camera Corner, many others. And so it's just a really fantastic place to be if you're into astronomy. Here at Explore Scientific, we've got behind me is the Explore First Light series. These telescopes are intended to get you started in astronomy, whether you're interested in deep sky or planetary. We've got it all. And so we're really happy to be here with you, and please come and visit us.
We're live here at the NEAF conference in Suffern, New York, and we're from Lowell Observatory. And Lowell Observatory this year is a great year because we're celebrating our 125th anniversary. So 125 years of great discoveries, and that's really the legacy of Lowell. We've been doing important research from the discovery of Pluto to VM Slipher's recessional velocity work to current research using our Discovery Channel telescope to discover planets around other stars and a lot of other great work. So we're doing a lot of great things, and it's also a great place to visit.
And we're doing all kinds of neat things this summer to commemorate our 125th anniversary. So we have coming soon the opening of our Giovanni Open Deck Observatory, which is going to feature 6 modern telescopes fully dedicated to public observing. A great suite of instruments there and some nice interpretive locations to look at and learn more about the telescopes and astronomy. And then of course this summer we're also celebrating the lunar legacy for Flagstaff as we approach the 50th anniversary of the lunar landing.
And it really is a great time to celebrate the 125th of Lowell and the 50th of the first moon landing, and all the astronauts who walked on the moon trained in northern Arizona. And so we have a community-wide celebration at Lowell Observatory and other science centers. Even our businesses are getting into it, creating specialty drinks like the Earthrise cocktail and a special moon pie and all sorts of other great desserts. So it's a really great time from now through the end of 2019. We're doing this Lunar Legacy celebration, plus all the stuff we normally do at Lowell. And we're also opening this new open deck observatory that Danielle mentioned that's going to change how we do astronomy outreach, because we have big 32-foot-long telescope to look through, plus this suite of state-of-the-art telescopes that our visitors can really see what it's like that real scientists do, and also just the wonder of looking through an eyepiece and gazing in awe at the universe. It's just something that we as humans
And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Hey, thank you very much. And welcome back to the NEAF Talks for this afternoon. I want to welcome you, and I also want to take this time to extend a big thanks to Celestron for promoting this next speaker. It's truly an extraordinary opportunity. I'd like to give them a big shout out and applause, because this truly is going to be great. Our next speaker, I have to say, maybe with the exception of the astronauts, has probably traveled the longest distance to get here. Okay? And with that, I want to say that this opportunity that he has to offer us is extremely important, and it's a great opportunity, what he has to share with us. He is an accomplished imager. He shares a lot of his intelligence and learnings online through various media methods. And I would like to take this time to welcome to NEAF, Mr. Dylan O'Donnell. Thank you. Thank you, Dylan.
Wow. There are way too many people here for this talk. Thank you for having me, and it's a real pleasure to be here at NEAF and meeting so many people. I feel like sometimes I'm in the backyard twiddling knobs and pushing buttons and ranting at a camera in the dark, and it's really comforting to know that I'm not the only weirdo, that I'm here with a room full of weirdos. When Celestron told me that I could come here and give this talk, and they gave me the brief, I had to ask them. I said, let me get this straight. You're going to pay for me to come to New York and talk to a room full of mostly Americans about how good I've got it in my hemisphere? I'm born for this. This is my shtick. This is my whole shtick. I was born for this moment. This is fantastic. So the title of the talk, of course, is The Tour of the Southern Skies. But as I was writing the talk, in my head, the working title was, my hemisphere could beat up your hemisphere any day of the week. I should also ask, can anyone understand a word I'm saying? Yeah. I realized that my accent's a little different, and I wasn't sure if it was like a New York thing, whether I just wasn't speaking loud enough, or if I really do sound like Crocodile Dundee. But why should you care what I have to say at all? At the end of the day, I'm just a guy with a telescope, just a guy who walked into a store and bought a telescope. If you Google my name, I've worked really hard over the years to make sure that I come up first, and I've been optimizing those results. I ego Google regularly, have my news alerts set up. Unfortunately, there's one guy that will come up. He's an English footballer called Dylan O'Donnell. I've been working really hard to edge him off the page. He's recently changed his name, so I like to think that I've had something to do with that. But I don't want to bore you with just a normal slideshow. There's nothing more boring than talking about someone's travels or someone's slides in general. I have a master's in information technology, so my background is in computer science, and I'm halfway through an astronomy degree. But ultimately, I am just like you guys. I'm just someone who bought a telescope, and I really have to thank Celestron for the support they've been giving me over the years. This is just my Instagram, basically. This is the Instagram for the last couple of years, so you can see the improvement and the progression. This is a couple of years old now, but I've taken a lot of photos, and that's probably the only thing that really qualifies me to be here, other than the fact that I live in the Southern Hemisphere. That qualifies me more than most of you guys. I do have a couple of APODs. I don't really do it for APODs and award ceremonies and things like that. I give away my work for free as well. You can choose to license your work as Creative Commons, but I choose public domain because with public domain, people don't have to give you credit. They can take that image and they can use it for anything. And that means sometimes my images get taken and they get put on, flat Earth stuff, and they get put on anything. But it also gets picked up by news organizations. It gets picked up by all sorts of outlets who feel free when they're running to a deadline to use my images. So if you are an astrophotographer yourself, I do highly recommend considering public domain. Get your images out there for free. We're competing with NASA, and they give their images out for free. So I don't see why I can put a price on my stuff. I'm lucky enough to live in Byron Bay in Australia. It's this beautiful hippie paradise on the easternmost point of Australia. It's a kind of wealthy paradise now too. We've got people like Matt Damon and Miley Cyrus and Chris Hemsworth living in their multi-million-dollar mansions out there. But it has this real hippie ethos about the whole place. It's a really beautiful place to live. It's still illegal to smoke weed over there, but everyone does. But we are lucky to have the first sunrise and the first sunset in the country because we are that easternmost place. It's a special place for a few reasons. Because of this hippie ethos it has, it's very anti-development. So there are no buildings over 3 stories. So you can sit on the beach and look back and you just see trees. It just feels like you're in the middle of nowhere. There's only 6,000 people living there, but we have 2 million people just coming through the town every year. Someone in the 1990s decided to bury the street lighting, and this had this cool effect where you're in the urban streets and the street lights are just gone. You can see houses and you can see the Milky Way over the top of it. So very low light pollution. They don't like capitalism generally there, so they won't let McDonald's move into town, for example. But they're also afraid of fluoride and vaccinating their children, so it's a bit weird. It's a bit like San Francisco, where wealthy hippies reckon they can be a bit anti-science, which is a shame. And it's ironic because I care about science and I care about astronomy, and I'm the astronomer in Byron Bay. But when I tell people that I'm an astronomer, they say, "Oh, that's lovely, I'm a Virgo." They really don't care. So these are my skies. This is most of the reason that my photos are okay. I have good skies. I estimate for my house I'm probably Bortle 2.5, which is in between a rural location and a truly dark sky. The town has a small glow, and that's certainly a factor. But when you're looking east, you're looking towards nothing. There's nothing for miles and miles, like 8,000 miles. Nothing's there. So here I am, just some guy living in a hippie paradise, and I walk into a store one day and I buy a little Celestron 4SE, which at the time I thought was a really expensive telescope, and I was in for a surprise. And here's an image that I took riding piggyback on that telescope. I was doing everything wrong, so this is one of my early images, but you can see a really dense part of the Milky Way. But I wanted to show you this because I wanted to show you that even though I didn't know what I was doing and I was just starting out, it's super easy. It's just super easy to go wrong down there. So this is with a cheap DSLR camera, 4 45-second shots stitched together, showing from the core of Sagittarius all the way to Scorpio and Carina, and just blazingly bright. This is high above us, so it's not over on the horizon, it's like right up. So it's beautiful to photograph. The core area rises over the ocean, just goes straight up, and then comes right down over the west. So you've got a huge segment of the night to try different things. And the Dutch astronomer, Bart Bok, Dutch-American astronomer, he's famous for saying all the best stuff is in the southern hemisphere. Bart Bok is the guy who coined the term Bok globules. So if you've ever seen nebulas with Bok globules in them, they're named after that guy. And it's always nice when an American tells us that we're better. Now that might come as a surprise to Charles Messier, who observed and catalogued mostly from France. And you can see that he left a huge gaping hole in the middle, or the bottom, I should say, of his catalogue. He basically left us off the catalogue, which is sort of funny for us in Australia. We know that if something that we're photographing doesn't have an M designation, that it's something that you guys can't see. So we lean heavily on the NGC and the IC catalogue. Now this is me underneath Carina. I'm well and truly in love with Carina. I was calling Carina my girlfriend for a long time. She's very, very easy to fall in love with. And if you look at Wikipedia, it tells you that Carina was discovered in 1752 by a French dude, which is, I guarantee you, it wasn't discovered by a French dude in 1752. It's been there the whole time. It's literally the brightest, biggest thing you can see in the sky. And we've known about it for a long time before that. So yeah, naturally it features in Aboriginal history and Aboriginal astronomy and tradition. Now, I know you guys in America love big things. We're all about big things here. I don't know how you guys deal with those medium-sized servings. They feel like they are bigger than my internal organs can handle. But we like big things in Australia too. So we have the big rolling pin, the big sheep, the big banana, and the big prawn, which are classic highway icon truck stops In fact, those are the directions to my house from Melbourne, if you ever need to know how to go. So, let's go through what you can see. Bullet point list for the southern hemisphere. We have the brightest, biggest nebula visible from Earth, which is Carina, of course. We have the brightest, biggest naked eye galaxy, which is a large Magellanic Cloud. You don't need any equipment to see that. The brightest, biggest part of the Milky Way, the core, of course. The darkest, biggest dark nebulas, the Coalsack Nebula, Emu, Rho Ophiuchus, and a whole slew of dark nebulas through those regions. And we have the brightest, biggest globular cluster, if you're into globular clusters. And we still get to see Orion upside down compared to what you guys see it, but we still get that too. So we get a lot of good stuff. This is a photo that I took from Western Australia. An important aspect of astrophotography, especially this wide field Milky Way stuff, is the landscape. And you guys here have a very diverse landscape. You guys have the Grand Canyon, you have mountains, you have snow, you have desert, you've got everything. And Australia has a lot of that too. We just don't have the big mountains that you guys have. And the pinnacles in Western Australia are beautiful. And none of this is locked off. You can just drive your car into it at any time of the year, any time of night, and just get out of the car and take photos. This image is interesting because I made a mistake, a beginner's error on this image. There's a setting in your camera where you can turn down the size of the image, and what that effectively does is bin the image, so everything becomes twice as bright, and that's what happened here. But I think it really illustrates just how bright and beautiful we have it down there. You've got the Coalsack Nebula up here, and of course the large Magellanic Cloud and the small Magellanic Cloud there. It's a beautiful example as well of constellations. I've always thought of as a bit weird. Maybe it's because I'm a new astronomer. I don't really care about the constellations. I know that's a bit weird to say, but when you're out there on a dark sky, good luck finding a constellation. You literally cannot make them out. Now, sometimes, and I've heard this story a few times, you'll be out there imaging or observing with someone, and you'll say, it's a beautiful, clear night tonight, look how clear we've got it. And they say, it's pretty clear except for those clouds over there. And then you have to explain to them, they're not clouds, they're nearby galaxies. And that's funny, but that happened to you guys as well in the big blackout of 1977, I believe, in New York, where people actually called 911 because they thought the city was on fire because of this big trail of smoke across the sky that they'd never seen before. Oh, so Omega Centauri. Just for scale, that's Omega Centauri up there. And next slide, you can see it's big, right? You don't need any equipment to see that either. And that's Omega Centauri there. But you know, how boring are globular clusters? Well, you've seen one, you've seen them all. If I hadn't have shown you that last slide where it showed you the scale, a globular cluster is a globular cluster. But they do have some interesting science. They're kind of very mysterious scientifically. They're filled with old stars, but they don't follow the plane of our galaxy. So our galaxy is flat, the Milky Way is flat, but the globular clusters are all over the place. We don't know why, we don't know how they formed, we don't know how they evolved. They're a really strange object. So in that sense, they're very interesting scientifically. I should say how intimidating it is not to be here and talking or anything like that, but just showing images at NEAF to people who are experts in taking images. And so you guys probably already can see that my chip is tilted here and I have some out of focus stars there. So I'm going to admit to all of this stuff as I go. Now this shot is the Large Magellanic Cloud with no special equipment, just a DSLR literally out the back door. So I've gone out the back door, put the DSLR there, done a few 30-second exposures, and caught a comet flying past the Large Magellanic Cloud. Now I mentioned that I made my images public domain. So I take something like this, it's an event, I put it online, and the next day I had the editor from, or one of the article journalists from National Geographic take that image and publish it because he was doing a particular story on comets and that particular comet. Now the elephant in the room, of course, is that you guys have Andromeda. I realise that Andromeda is prototypical perfect specimen. And our specimen is not so perfect. It is the Danny DeVito of large galaxies. I get that. So fair's fair, you guys can have Andromeda. And I will point out here, this little green spot here is the Tarantula Nebula. And that's a really cool thing to see in our nearby galaxy, is that we can image the nebulas within another galaxy somewhere else. And if you just take an image with your camera, it shifts into the green. I don't know why it's green, because we know it's hydrogen, and we know if we process it correctly, it's actually quite red and beautiful. This is taken with the 11-inch RASA. And the good thing about Tarantula as well down the south is that it's circumpolar, so it's always at the pole. And you find this, especially on our astronomy forums and things like that, whenever you're having trouble with something else, having trouble with Orion or having trouble with Carina, or everyone's backup is always Tarantula. Tarantula's always there in the sky. But we need to go deeper. So around the LMC, around the Large Magellanic Cloud, there's a whole bunch of little nebulas, not just Tarantula. This is an example of the Dragon's Head Nebula. Obviously, a lot of star formation going on, old stars, new stars, and I don't know what's going on here. There's a star that's shedding stuff. It's just really, really fascinating. Not a common one, this one, but one that I really like. So I have a bone to pick with New York City. Do you guys know what this one's called? It's the Statue of Liberty Nebula. But you guys can't see it. So we've got an object that's named after one of your most iconic statues. It's like if I call the Heart and Soul Nebula the Great Barrier Reef Nebula. So I'm thinking about it. This is taken with a Celestron 9 1/4. But I think it should be called the Breakfast Club Nebula. Because I don't know about you, but this is uncanny. We've got the part of the hair, we've got the glove, we've got the lapel, we've got the belt, we've got the flick of the coat. It's uncanny. So I propose that if we rename this the Breakfast Club Nebula, then I won't rename the Heart and Soul Nebula the Great Barrier Reef Nebula. Now over east, because we have this fantastic clear view out over the ocean, there's an effect that you normally only see from photos like Don Pettit's, where you're taking photos from the International Space Station, and you can see that thin sliver of atmosphere. And you can see that that thin sliver is glowing green. And that is our glow. That's the glow of our planet. And it's very hard to capture unless you have a super deep sky. And I'm lucky because I can see the horizon as well going out over east. So it's a very special phenomenon you can get with these wide-field Milky Way shots. So I want to talk quickly about the dark nebulas that we can see out there. This is Corona Australis, which I like because it's named after my country, the dark molecular cloud. There's so much going on in this nebula. It's big, it doesn't even fit into this frame, which is taken with, let me see, what's this one taken with? The RASA 11-inch, 30-second exposures, under an hour. So I've knocked this image out under an hour, which is what the RASAs are good for. And you can see up here, we sometimes call this guy Yoda. So that's Yoda's walking stick. He's holding a little walking stick there, it has two eyes. And Australia literally means southern place. So here's a little map I found of the celestial sphere, just to give you an idea of where everything is. You guys can see all your northern stuff up here near the pole. Both of us can see Orion because it's near the equator there, the celestial equator. And they didn't actually have much stuff to put down here. So whoever did this map is probably from the northern hemisphere. But I thought that would give you some perspective anyway. This gives you an idea of how much stuff is just in that dense region. It's just nebulas galore. So when I think you guys call it the galaxy season coming up, and for us it just goes from nebula season to more nebulous season. It's pretty mental. And the next slide is Rho Ophiuchus. You guys see this one, but I think it's a bit lower on the horizon for you guys. So this is pretty easy to take photos of. This is just piggybacked, so not using a telescope, just a Canon 200mm lens, 30-second exposures. I think this one is tracking, but it's not guiding, so pretty simple. but let's go a bit deeper. So you can see same area, just in quite a bit. So that's taken with the Hyperstar and the Celestron 9.25 Edge HD. And notice how I am, throughout this presentation, I'm changing focal lengths. And often we get into the trap of buying a setup and just like adding so much stuff onto a setup. You get focuses and you get rotators and you get all this stuff. But that actually makes it hard to change, chop and change. And what I like to do is I change telescopes, I change cameras, I change focal lengths, use reducers, don't use reducers. You get much more diversity in your images. And even though I'm taking an image of the same region, it's like a completely different photo, a completely different kind of feel to it. And sometimes I don't use telescopes at all. This is the Coal Sack Nebula, which is the head of the emu in Aboriginal culture. And this is my incredibly urban situation. I'm up against fences, there's a street light up here somewhere, and I've got palm trees in the backyard. Basically, I can't see the pole. All I can see is straight up and across over the neighbour's fence. But that gives you an idea of the kind of urban situation I have, even though I'm in hippie paradise Byron Bay. But it also means that I have a time pressure. So when I'm imaging, I really love the F2 imaging, and this is why I've done so many videos on RASA, why I was so quick to take up Hyperstar in the first place. I don't want to spend like the whole 12 hours overnight doing astronomy. I want to knock out an image in a few hours and go to bed because I have kids who are going to jump on me at 6 o'clock in the morning. This is not one of mine. This is by Corey Schmitz from South Africa, I believe. This is called the Dark Doodad, which is a very imaginative name for a dark molecular cloud. But again, I just wanted to show you that all of those dust lanes in and around the core of the Milky Way are super populated with all of these dark nebulas, and they can be just as fun to take photographs of as the big bright nebulas as well. So we get on to my girlfriend, Karina. I really love this photo. It's taken in the Hubble palette, but I didn't push the green as you sometimes naturally want to do in the Hubble palette. This is taken with the 11-inch RASA, and again, it's a photo I've just knocked out over one night, so one session. Now, to give you an idea of scale, Orion is about 1.5 times bigger than the Moon, and Carina is 4 times bigger than the Moon. And that's just the core sort of area as well. This stretches out way past the front, and you can see that it's stretching out way past the front here as well on the 11-inch. And this is just taken in 60-second exposures as well. I find with the RASA, I love to push it, so I love to do like 5-10 minute exposures on the RASA just to get some of the insane faint stuff. But I find that blows out the stars, especially when you're in a region like this or a dense region like the Milky Way. All the stars just tend to be fat, so I tend to stick to 30, 60 seconds. So this is the same area on the RASA 8. This is the RASA 8. This has been such a great scope to get a hold of and play with. And you can see it still doesn't fit the whole of Carina. This is at 400 millimeters. So if they want to fit in the whole of this object, they'll actually need to, I don't know, get a RASA 6-inch, RASA 4-inch, Megastar 4-inch RASA. I don't know. It's a huge target, and I really love it. And I should say that the reason I take okay photos is because I have this stuff which is just so bright, and I'm using gear like the RASAs. There's really no way I can go wrong. You could be doing this unguided if you wanted to. I tend to guide and dither and all that as well, but this can be unguided. It's pretty easy. The gear and the targets are doing all the heavy lifting for me. This is Carina in natural color, taken with the 11-inch. And you can obviously tell a natural color image because you've got the blue stars and the orange stars. They all kind of get a bit weird when you're doing the narrowband stuff. But if you're closer to a city, narrowband is really your only option, which is why it's good to see that the RASA 8 will work with the narrowband filter draw system from Starizona. And I can see that that particular setup has been hugely popular already. So it's an option. You don't have to have dark skies like I do to take images like this. This image could have been taken, not this image, but the last narrowband one could have been taken from the middle of Sydney or New York. So we need to go deeper. This is Carina not taken with a RASA. This is Carina taken with the 9 1/4. So we're zooming in to the region here. And there's so much to look at. Even in this one target, it's just filled with different stuff. And so I've tried to annotate it to give you an idea of some of these things, because some of these areas are famous Hubble images as well. We've got the Dusty Mountains, the Treasure Chest, the Keyhole, Ida Car, and this one is a famous Hubble photo. That one's a famous Hubble photo. But I think my favorite Hubble photo from this region is God's middle finger. And that is a Bok globule as well, which was named after Bart Bok. Just a fantastic section. Now, in that same area, Ida Car itself is a fascinating star. It's a candidate like Betelgeuse for going supernova. They don't really know when it's going to go supernova. They just suspect, based on its age and the evolution of stars, that it should be due sometime soon. And in the 1800s, do I have the year here? 1843, it became the brightest star in the sky. So that was an event that was witnessed all around the southern hemisphere. And it's this flaring that happens. The star shed a bunch of stellar material and flared up and became the brightest star in the sky. And we can still see the remnants of that here. But that sort of shot, I had to find one online because I haven't done this myself. It's on my bucket list. This is the sort of shot that you'd take the same way you do planetary, the same way if you were taking a photo of Jupiter or Mars. You'd be doing video imaging on this. So you'd want a really long focal length and try and find that star and then be taking video to stack the video. This is taken with a C14 Edge HD and an ASI 224 MC and taken by a Brazilian guy called Ivani Soares. He used a 1.5 minute video. And what's also special about this is that we now know it's going to be gone in 10 years. It would be really interesting to see someone animate this or take photos of this over the next 10 years and stitch them together in an animation, because we're seeing the last death throes of a star before it goes supernova. There's some argument, of course, as to if it goes supernova, will it have an effect on life here? The naysayers say it will wipe out our ozone layer and kill us all. But it would probably just look really cool and really cool to photograph, and I can't wait. This is another beautiful region of space, the Fighting Dragons of Ara. And this is also in the HST palette, so the Hubble Space Telescope palette, taken with the Celestron RASA in 60-second exposures. It's about half the size of Carina, but still twice as big as the Moon. So it's bigger than Orion still, but not quite as bright as Orion. So a massive, massive area, but we need to go deeper because I'm changing focal lengths again. And that's the same region taken in true color. And you can see how different these photos look. They're the same thing, basically just different focal lengths and different color treatments, one in true color and one in the Hubble Space Telescope. So a little closer up. We have some famous galaxies. There is the Sculptor galaxy there. I find galaxy work really hard, and I'm not a galaxy guy, as it were. But when you're taking photos of galaxies, you of course want to take the hydrogen alpha and lay that over your RGB, so you can see those beautiful red jewels popping out of your image, and you can get all that beautiful nebulosity coming through. We have this other weird galaxy called Centaurus A, or sometimes called the Hamburger galaxy. And we're still arguing over what it is. It's really weird looking. It's not like any other galaxy. It's definitely not the Arnold Schwarzenegger, and it's not the Danny DeVito even. It's just super weird. And it's really close. And it's close enough that we can study it quite well. And it has very strong radio emissions. But it might be, because it is this close, that we find it weird. Because unlike the other galaxies, which are quite distant, we've got a very good view of this one. And because of that, we can't figure out whether it's elliptical or regular or what it is. And this was discovered in Sydney in the 1800s by a Scotsman. But the only thing you'd discover in Parramatta these days is probably a hypodermic needle or a parking ticket. This is the Milky Way core. It's super dense. You guys can see this too, and I see images of M8, the Lagoon Nebula, and the Trifid coming from here. But again, just a little lower on the horizon for you, and it's just straight up for us, which makes it really easy to take photographs. And you can see the dense star field is just something to behold. This is Saturn running through here, M8 and M20. And it's when you're imaging like this and you put your guide camera on, there is no trouble picking a guide star. Your little guide camera is just full of stars. It's really quite something. This was taken with 30-second photos and a 200mm lens, so it's not even through a telescope. It's just riding piggyback on the CGX. Now, this is our South Celestial Pole. Do you notice anything different about our celestial pole compared to yours? The pole star. You guys have a bright star right in the middle, which makes it super easy for you guys to align your telescopes when you're at a star party. And we've got nothing. And I told you before how useless constellations are. When you're out, good luck finding octans. It's invisible. So we go out to star parties and we use all sorts of weird and wonderful methods. Of course, we've got our compasses out and we're trying to work out the offset, and we've got sticks in the ground to see the shadow at a particular time of day and work that out. But if you go to a star party in the southern hemisphere, everyone's screwing up on the first night, and by the second night they've got their polar alignment worked out and everything's running fine. But I do truly recommend the Celestron All-Star Polar Align method. That's always worked for me very well. So this is taken in Western Australia. You can see the large and small Magellanic clouds as little fluffy blurs there. And this is taken at the DSA-1 tracking station. I was lucky enough to be commissioned by the European Space Agency to go do some photography of their dish over there. And we've got a few good big dishes in Australia. And have you guys seen the movie The Dish? Know of it? If you haven't seen it, it's about the Apollo mission, and it's about the fact that when Neil Armstrong was stepping onto the moon, those live images were not coming to you direct from NASA, they were coming to you direct from Parkes, where the big dish is in Australia. Because any space agency needs to be in contact with their satellites all the time, there has to be at least 3 dishes on each side of the planet so that they can remain in contact. So Australia has a bunch of these dishes for various space agencies so we can remain in contact. And as Neil Armstrong came out of the module, our dish was at its limit. It was literally standing up on its side, and they just managed to make contact. And it's a very good movie. You should see it if you can. It's called The Dish. There's a whole bunch of moon's conspiracy theories about the tapes from that mission, and that they'd been doctored through Australia, and that we were sending computer graphics through, and it was all fake and all that. But a guy called John Sarkisian from the CSIRO won the Order of Australia, which is a medal from the Queen, for doing all the research to try and find where these missing tapes are from this mission. And they never found the missing tapes, but it could be, they think they've either been destroyed or it's at an ex-employee's house and they can't get a warrant to get into this guy's house. So the moon conspiracy theorists obviously take that one to town. Speaking of the moon, I'm sort of known for moon photography, which is ironic because I kind of don't like the moon most of the time because I'm a deep space imager, but I have taken a few nice transit photos. Obviously you guys can see this here too, and you guys can do this too. But when I first got into astronomy, taking a transit photo was the furthest thing from my mind. I'd read about it in magazines, astronomy magazines and whatnot, but I thought, that's crazy. How could you possibly do this? It was like some sort of dark art. But then after a while, I got comfortable with using my gear and I tried it and it worked. And I just couldn't believe it. So I have made videos about this and how you can do it as well. And it's really nice when people come up to me and they show me their transit photos and that I'd help them do that. This is one that is on exhibit this year at the Hudson River Gallery. So I'm actually exhibiting in New York, which is super weird as well. And Tim Peake was on the space station at that time. But this is probably my most famous transit image. This is the one that went viral and when people started to notice me a bit more and when I climbed the ranks of Google for the search Dylan O'Donnell. And it got picked up by mainstream media and it got retweeted by the International Space Station. Chris Hadfield was getting asked questions about it in interviews and stuff like that. It was really amazing. But I don't know why, I don't really know what makes something go viral, right? We don't expect to go viral and we don't know why it happens. I suspect it's something to do with the way the space station is positioned near the craters and near the Terminator, and also that I process the image in colour as well. We're used to seeing very monochromatic images of the moon, but the moon has a very natural colour that you can bring out quite easily just by pushing your processing a little more. So here is the moon at sunset for Stonehenge and New York. So you can see something weird. They look backwards, don't they? This is not the way we normally display them in classical literature and paintings and things like that. The moon normally is pictured like that. And that's not something I've just noticed. It's something that The Simpsons do as well. So it's always been a mystery where Springfield is, but astronomers have studied The Simpsons and we've worked out that it's in New Zealand. So all this time you guys have been saying that my photos of Orion and my photos of the moon are upside down. Turns out you guys have been upside down this whole time. This is a pretty stark contrast. This is the difference between the light pollution in America and Australia. You can see if you're in the middle of Australia, it's dry, so the skies are clear pretty much all the time, and there's no light not just near you, but for miles and miles. I'm lucky enough to live on the easternmost tip, so I'm about here, so I'm well away from the cities. Any light pollution in the town is you walk out the back door and out the fence and across the street and you're out of the light pollution, basically. It's very easy to photograph. This is the middle that I was talking about. So in the middle of Australia, we have Uluru, which is a big rock that we don't really understand. And it's a beautiful thing to photograph. Now, I was looking at traveling there to do photography like this, and I saw a Facebook ad that said that I could go on a tour there for $3,000. I thought, oh, that was interesting. And I clicked in and I read the fine print and it said, does not include flights. So I'm thinking, well, what's the $3,000 for? And I did some more research and found out that the rooms are only like $100 a night. So you don't need to spend $3,000 on a tour to get an image like this. You just go and get the $100 a night room, wait till it's dark, and walk outside. It seems like a bit of a scam. Anyway, this is Uluru. Also near Uluru, we have an American military base where we help America and New Zealand and Canada and England spy on all of your emails and store everything so that we are part of the Five Eyes spying and data collection. And we don't know when America comes in and out. They can just go and leave whenever they like. It's a very interesting part of the world. Also, you can get meteorites there. I've spoken to Jeff Notkin about this, the meteorite expert. If you walk out into the desert with a magnet, you will find meteorites. When meteorites fall by the coast or in wet areas, they rust and they'll disappear after a while. But here in the middle of Australia, not only will you go and find dark skies, if you just walk around with a magnet cane or a large magnet, you will find meteorites. Now, there are other things to contend with in Australia when doing astrophotography. This is a black and white bandy snake that I almost stepped on while going out to get a Milky Way shot. There's a green tree frog that I found on my Celestron tripod as I came out to check the imaging run. There's a python that was in my tool shed as I went to get a screwdriver. I've also had pythons on the fence next to me while I'm imaging that you just don't see until you turn on the light after the night's imaging. But they're mostly harmless, and they're harmless enough that I will trust my young boy, Zenon here. This is my son holding an adult python with a broken arm. That's a pretty Australian photo, don't you think? But the other day I came out to my rasa and found that a giant bat had defecated all over the mirror. They eat these fruit berries and then they crap them out, and so a lot of people ask me how I cleaned it. And I cleaned it very, very carefully because if you scrape, you could have scratched the glass. And there's that same snake, which I said was harmless on the last slide, eating one of those fruit bats, which I don't mind at all. Now, I am mostly into pretty pictures, but I am doing an astronomy degree, and I do dabble in the sciencey side of things. So every night, there is a list of objects that have been discovered. And this is happening right now. And this is a live website. I can give you the link if you need it. It's on the video about this. But the Minor Planet Center shows us the things that we've discovered moving in the sky each night. And any given night, there might be 20 or 30 things which are brand new to us, brand new to science. We've never seen them before. And it's hard. This list was hard to pass. It was just a list of numbers. So I thought, I'll take the numbers and I'll write some code and I'll make it so that we can actually see what's going on. Because I wanted to see if there was any of these things I could do follow-up observations for. But when I did it, I found something really interesting. And that was this huge bias in the data. I mean, the first bias is the fact that it's just a big strip, right? So that's a time of night. That's a time when they turn on the telescopes, do their survey work, and then turn them off for the night. That's one bit of bias. The other bias, of course, is that we have things clustered here around the equator. Huge cluster, bunch up north, and a few little observations down south. So what's causing this bias in the data? And the bias is caused mostly because the two primary surveys now are Pan-STARRS and Catalina. So they're doing most of the heavy lifting for this, and you can see where they're located here. I should show you as well the locations here. We have, this is obviously happening around those survey locations in Hawaii and America. That white dot there is where I am, so I could tell if I could follow up on any of these. And the yellow bar here is where Bruce Willis is at any time, in case we need him to deflect a meteorite. and that's funny, right? But if you look at this graph, Armageddon the movie came out here. And funding, Congress suddenly said, we need funding to find out where all of this stuff is, because they became suddenly concerned about the impact of asteroids over 1,000 meters or 1 kilometer. They reckon they found about 80%, which doesn't comfort me too much. The funding continues, but unfortunately my country just dropped out, and for political reasons, politicians want to divert money to other things. I think our government's spending $250 million on advertising themselves this year. So that's funding that was pulled from CSIRO, our space agency, our science organisation, and funding for that blind spot. Because this is a blind spot. In the southern hemisphere, there is a gap in the data that you can see there where there could be things happening. There could be asteroids that we haven't discovered. There could be potentially hazardous asteroids that would change life on this planet that we simply can't see. And that's an opportunity. It's an opportunity for me. It's an opportunity for any astronomer in the southern hemisphere. A friend of mine, Terry Lovejoy, has a Celestron 14 with Hyperstar, and he discovers comets from his backyard. He's discovered 5 or 6 now. And the reason he can discover them is because he doesn't have to compete with the big surveys, because he is exploiting that gap in the data. And the other thing to note is that if you discover a comet, it gets named, you get your last name after it. So it's Comet O'Donnell, Comet whatever. And it's there in perpetuity for history. Every time this comet comes back, long or short, it's named after you. Now, I did propose that you should, what we could do as astronomers is go to companies like McDonald's or Coke and convince them to fund an observatory. Because if they found a comet and it was called the McDonald's Observatory, they would get the credit. And then for history, they would be called, Comet McDonald's or whatever coming through. And I had people who were absolutely horrified at this suggestion. And a lot of professional colleagues just said, that's disgusting. And I sort of said, well, I don't really care who's paying for it. If you can trick a company into paying for astronomy gear and searching for the missing 20% of asteroids which may or may not cause extinction on this planet, that's fine by me. I don't really care what the asteroid's called at all. So anyway, my name is Dylan O'Donnell. You can find me on Instagram. You can find my videos on YouTube. I run a festival in the Southern Hemisphere called Star Stuff, where you can come down and see the southern night sky and hear lots of cool speakers as well. I'll take some questions, but remember, everything is meaningless and we're all going to die. I think, is there a format for questions? Do you just sing out, or? You've got a question up the back here. So what I tend to do is a trick with one-shot color, but then I use HA as the detail layer, so the luminance layer. So I tend to use HA RGB. You just get way more detail that way, yeah. That's the way I tend to do all my true color images. Often in the same night, yeah, because it's imaging at f2, so you just swap the camera. I'll use the same setup, take the hydrogen alpha narrowband mono camera off and put the RGB camera on, and that works great. It's a real kind of shortcut, yeah. Any other questions? Yep.
Obviously, there's this real northern hemisphere bias like you were talking about with an SCA catalog and how that came about. And you said that you just look for NGC codes in the southern hemisphere. Have you ever thought about making just a southern hemisphere catalog?
That would be cool. Yeah, we could have a catalog that excludes all of you guys and just have our stuff in it. I like that idea.
Comparable objects, faint fuzzies that you don't need heavy gear to find.
Mm.
You say, oh, this is, O'Donnell 1, O'Donnell,
The O catalog. I am so into that idea. No, I think that's an excellent idea. Thank you for that. I think there's another question up there somewhere. No? Are we done for questions? I think that's it. Thank you very much. Oh, one more. I cannot image from New York. I don't know how you guys do it. Thank you very much, guys.
Hey, thank you very much. Thank you very much, Dylan. Great job. Great job. Thanks.
There is not another field of human contemplation so wonderfully rich as astronomy. It is so easy to reach, so responsive to every mood, so stimulating, uplifting, abstracting, and infinitely consoling. Everybody may not be a chemist. Everybody may not be a geologist or a mathematician, but everybody may be, and ought to be, in a modest personal way, an astronomer. For stargazing is a great medicine for the soul.
Take you on a journey to the outer reaches of the solar system.
Mission Operations Manager, as a mom.
It's great to be here. Thank you. Wow, there are a lot of you. Conference.
Friday, I was a launch chief engineer, and that means that I'm really busy with the mission.
No one has ever seen before.
My name is Grant Regan, and I live in Los Angeles. I first got into astronomy. Just as a kid, I was always interested in the sky. I'm situated on the west side of LA, and the light pollution is pretty bad anywhere in LA. And even if you drive an hour and a half out, you'll still see the light dome of LA in the south or in the north, depending on where you go. The ROSA 8 has a very fast system, and because of that, you can take images that would on other scopes take up to like 30 minutes. You can take on the ROSA in a minute or less. And that difference is huge, because what matters is that you can take short exposures but get that detail and not have star trailing or anything like that.
And basically I'm taking this from a heated car when it's almost freezing outside. There's a telescope right there, so I'm just remote control using it. This is just a lone exposure. It isn't even a raw image. It's not processed at all, so once we process these, they're gonna look amazing.
With astrophotography, it's not just taking a shot and saying like, this is what's on the sky. It's really taking multiple shots, stacking them together, and putting your own vision on that and showing how you see the sky.
Hi, my name is Jeff Norwood. I'm the owner of Camera Concepts and Telescope Solutions. We're based in Long Island, New York, and we are, I'm proud to say, one of the supermarket vendors of telescopery. We sell everything and everything, from accessories to screws and bolts to things you need at star parties, all the way up to Takahashi's and you name it, all the rest of that. So at our booth here, we've been coming here to NEAF for over 20 years. We basically bring the entire store with us. So we've got lots of goodies. And of course, everything's on sale, great deals. Our website is www.cameraconcepts.com. Please visit us. We support what we sell. We've got experts in the field on staff to help you with astrophotography or all your visual aids that you might need. So thanks a lot, and bye.
Hi, I'm Kelly Beatty from Sky and Telescope. I'm a senior editor on the staff. I've been on the staff of Sky and Telescope since 1974, hard to believe. But I'm still having fun, and why wouldn't I? We're a very important part of the amateur astronomy community, just as NEAF has become a kind of essential go-to place each year for many thousands of people in the amateur community. We're here, we're one of the co-sponsors of NEAF, and we are dedicated to being a major part of that. You know, people think of us as just Sky and Telescope magazine. We're actually much broader than that in a couple of respects. One thing is we do a lot of outreach. We provide a lot of materials for amateur clubs across the country when they need materials to distribute at their star parties and such. And we also do some products that are maybe not what you'd expect from a magazine. I've got a couple here. We have a whole line of globes that we sell. They're really great. This one, for example, this black beauty is our celestial globe, which shows all the stars in the sky down to 5th magnitude. And then this is our new one, just about to be produced. It's a globe of the Earth, obviously, but it shows all total solar eclipse paths until the year 2100. So if you're the kind of person who likes to plan ahead, this is just the globe for you. You'll know where to be in 2024 and beyond. The other thing we do a lot of is tours. Speaking of those eclipses, we've actually got a whole bunch of tours that we do all over the world. We just had a tour finish in Finland to go see the auroras. It was very successful. This summer we have a tour of Chile coming up for a total solar eclipse. We've got an observing tour planned for Australia that is just going to be killer. So for all these reasons, Sky and Telescope sort of considers itself the essential guide to astronomy. And again, we've been at this for 75 years, so we really have a good handle on the amateur community. We're from the amateur community. We'll always be a part of it. And we are so grateful to the organizers of NEAF, Ed Seaman and the rest of the crew here for welcoming us every year and being such gracious hosts in this amazing setting where the sky is really the limit. So thanks very much for the opportunity to chat, and we'll see you here next year.
Hello there, I'm Lonnie Weegee with Celestron, and we're here live today at NEAF, and I thought I'd show you one of our new products. So what you're looking at is a brand new Roe Ackerman design. We call it RASA. This is an 8-inch f2.0 imaging system. Now, one thing you'll notice about this, if you look at where we place the camera is designed to go on the front of the telescope. What we've done is we've taken a standard design and turn it into a RASA design, and that means the light goes through the corrector plate, it hits a primary mirror in the back, it's reflected back up on the camera, and we get very fast wide field images. If you notice the camera we're using, it fits inside the objective so we don't block any of the light. This has been a hugely popular product for us. We're unique in this design. If you're interested in wide field imaging, if you're interested in the sky surveys, if you're just interested in a good fast way to get started with astronomy, the Roe Ackerman is new. If you notice, we also have our new focuser on the back. This is something that's nice to have when you're doing astronomy and astro imaging. This will have steps that you'll be able to do the micro focusing needed to control a fast imaging system like this. We're very happy to have it here at NEAF, and come on by and take a look.
Hey everybody, Scott Roberts here from Explore Scientific, and we're here in Suffern, New York at the epicenter of the universe, the Northeast Astronomy Forum. This is a great event that happens every year, and it is in fact the world's largest astronomy trade show. Every manufacturer is here. You've got telescopes, you've got eyepieces, cameras, observatory domes, and tons of software. Some of the greatest retailers are here as well. You've got, Woodland Hills and High Point, Camera Corner, many others. And so it's just a really fantastic place to be if you're into astronomy. Here at Explore Scientific, we've got behind me is the Explore First Light series. These telescopes are intended to get you started in astronomy, whether you're interested in deep sky or planetary. We've got it all. And so we're really happy to be here with you, and please come and visit us.
We're live here at the NEAF conference in Suffern, New York, and we're from Lowell Observatory. And Lowell Observatory this year is a great year because we're celebrating our 125th anniversary. So 125 years of great discoveries, and that's really the legacy of Lowell. We've been doing important research from the discovery of Pluto to VM Slipher's recessional velocity work to current research using our Discovery Channel telescope to discover planets around other stars and a lot of other great work. So we're doing a lot of great things, and it's also a great place to visit.
And we're doing all kinds of neat things this summer to commemorate our 125th anniversary. So we have coming soon the opening of our Giovanni Open Deck Observatory, which is going to feature 6 modern telescopes fully dedicated to public observing. A great suite of instruments there and some nice interpretive locations to look at and learn more about the telescopes and astronomy. And then of course this summer we're also celebrating the lunar legacy for Flagstaff as we approach the 50th anniversary of the lunar landing.
And it really is a great time to celebrate the 125th of Lowell and the 50th of the first moon landing, and all the astronauts who walked on the moon trained in northern Arizona. And so we have a community-wide celebration at Lowell Observatory and other science centers. Even our businesses are getting into it, creating specialty drinks like the Earthrise cocktail and a special moon pie and all sorts of other great desserts. So it's a really great time from now through the end of 2019. We're doing this Lunar Legacy celebration, plus all the stuff we normally do at Lowell. And we're also opening this new open deck observatory that Danielle mentioned that's going to change how we do astronomy outreach, because we have big 32-foot-long telescope to look through, plus this suite of state-of-the-art telescopes that our visitors can really see what it's like that real scientists do, and also just the wonder of looking through an eyepiece and gazing in awe at the universe. It's just something that we as humans, it really captures our spirit. So there's a lot of great stuff like that to do at Lowell.
And speaking about looking through the eyepiece, there's nothing like looking through the 24-inch Alvin Clark telescope, refractor built in 96. So it's 123 years old this year, and we just restored it a few years ago. It's gorgeous looking through, and you can do that on Mars Hill in Flagstaff. So lots going on this year.
Yeah.
And we're here at NEAF in Suffern, New York, and looking forward to chatting with more people about Lowell's legacy over 125 years and all the neat things that are happening for our next 125.